Good afternoon, students. Let's begin today's session. So we'll continue with kinematics today. We were discussing about the particular case of motion in a straight line, and we'll continue from that point. We had talked about the application of calculus in kinematics, especially in kinematics along a straight line or for motion along a straight line, and we've seen a couple of examples. Now today we'll start with a very specific situation of uniformly accelerated straight line motion. So let's begin. Yes, so we will talk about uniformly accelerated motion along a straight line. So we'll start by understanding three specific equations that we can use for this. So you can think of this like a special case of straight line motion or special case of one-dimensional motion in which the acceleration is constant. So acceleration A, which is rate of change of velocity with respect to time, is constant or uniform. So if you visualize the acceleration versus time graph, that looks like a horizontal straight line. Of course, it can have either positive or negative algebraic sign. So in this case, I'll assume that it's with a positive sign. Now what that immediately means is that if rate of change is constant, it means that if I cross multiply the time and integrate this, okay, then at t equal to 0, suppose the initial velocity was u. So u here is the initial velocity at t equal to 0. And at time t equal to t, the velocity is v. So v is the instantaneous velocity at time t equal to t. Then we can further solve this like this, that here e is a constant, so it comes outside the integration symbol, becomes like this. Okay. So we know that integration of dx is x plus c. So integration of dx from, let's say, x1 to x2 is equal to x from x1 to x2. So that just becomes x2 minus x1. So likewise now what happens is that in this integration that we are going to do, on the left hand side, this will be v from u to v. Okay, and on the other side we have a into t, and this will be from t equal to 0 to t equal to t. So for the left hand side, the upper limit is v, the lower limit is u. For the right hand side, the upper limit is t, the lower limit is 0. So we have the relation that v minus u is equal to at, or that instantaneous velocity at any point of time t is given by this. So this becomes what is called the first equation of motion for uniformly accelerated one-dimensional motion. So this gives us, so this is the relation of instantaneous velocity v as a function of time. Obviously, u and a here are constants. So for example, if a particle starts from rest at t equal to 0 with a uniform acceleration of 2 meters per second square along a straight line, then using this equation, we can say that u being 0, a being 2 meters per second square, v is equal to 2t. So this is the velocity in meters per second as a function of time in seconds. That's a simple application. Okay, so I know all of you are familiar with this equation from class 9th, if I'm not mistaken, b equal to u plus at, but this is just the proper calculus way of deriving the equation, where it comes from, that b is equal to u plus at. It comes by application of definite integration and application of the definition of instantaneous acceleration. That instantaneous acceleration, which is constant over here, is defined as the instantaneous rate of change of velocity with respect to time. So dv by dt. Okay. So I'll just take you through the steps of this, make a note of the key points over here in the derivation. Okay, so I have shown you the integration that we've done to derive this from the side, also using the more standard language of integration that we've seen before, where the name of the variable is usually x. But now in this derivation, on the left hand side, the variable of integration is v. On the right hand side, the variable of integration is time t.
Sir,
Yeah.
so what if the acceleration is variable?
Then we have to use integration. So that's what I said, that we'll come back to that later. Last time we did a question based on that. I've given you variable acceleration and shown you how to do the integration to find velocity. Okay?
Yes.
But this right now we will be talking about this special case of uniform acceleration for the next few aspects of kinematics. Okay.
Okay, sir. Sir, can you please scroll down?
Yeah, I'm still.
So can you show the last part?
Yeah, the next part is a small example of this. Okay. So the derivation is first of all clear to all of you. Okay.
Yes,
So
sir.
we have plenty of application examples. Okay, people. So this is done. I hope no other questions and doubts, right? Okay, so now let's move on to the next equation that we get. So once we have this, that V is equal to U plus AT, okay, where we of course understand that U and A are both constants, and V is basically a function of time according to this equation. So you can also see that in terms of velocity versus time, the graphical representation, depending on whether our acceleration is positive or negative, okay, or therefore whether it is uniform acceleration situation or uniform deceleration situation, our velocity versus time graph. So I'll just take two examples, and from that we can work out these graphs. So suppose my initial velocity is let's say 20 meters per second, and my acceleration is plus 2 meters per second square. So as you can understand, the graph will be a straight line with a positive slope, and starting from a positive value of u, because so this will be 20 meters per second, and for example like at 1 second, it would have increased to 22. At 2 seconds it would have increased, so it will have a uniform slope, which is the property of a straight line graph. So this will be my v is equal to 20 plus 2t. That is the equation of this straight line. Now likewise, suppose I have an example where the initial velocity is again 20 meters per second. The acceleration is minus 2 meters per second square. So this is a case where we are uniformly decelerated. So it will be a straight line but with a negative slope. And right now I'm not worried about whether the object is finally coming to rest. So I've just taken some arbitrary time. The graph may go beyond this also, doesn't matter. Okay. So it's starting at 20 meters per second. Okay. And for example, say after 5 seconds, 5 seconds will probably be somewhere here, then it would have reduced to half its initial value, 10 meters per second, because here my v is going to be 20 minus 2t as a function of time. So v versus time graph is a linear or straight line graph in this case. Okay. It's a linear graph such that the slope of the graph delta v by delta t is equal to the uniform acceleration. That's the same thing as dv by dt, because that is the property of a straight line. As we have discussed earlier, linear functions have that property that instantaneous rate of change is equal to average rate of change, is equal to a uniform quantity or a constant. So all that, analysis in calculus that we had done before, all that comes directly into practice over here in this kinematic situation. So in motion along a straight line, you will see it is all about calculus actually. And when we come to two-dimensional motion and three-dimensional motion, it will become a combination of what we've learned in vectors, especially component algebra, along with what we've learned in calculus. Okay, so I'm sure the graph is clear to all of you, both the situations, the one with the positive slope and the negative slope. So you'll see that we have done more than enough work on graphs in our calculus, basic calculus portion, that we will not really have any difficulty following the graphs in kinematics. Okay, now next we move on to understanding the relationship between displacement and time. Okay, so we are continuing with the same situation, motion along a straight line with uniform acceleration. So now displacement as a function of time for the same uniformly accelerated 1D motion. In short form, we can just write it like this. Okay, so we have v equal to u plus at. Okay, so this implies that the instantaneous rate of change of velocity, sorry, rate of change of displacement is equal to u plus at, because v is equal to ds by dt. Instantaneous velocity equals to the instantaneous rate of change of displacement or position, you can say either way, with respect to time. Okay. So we can alternately also say that dx by dt is equal to u plus at, where x is position. So we come to both the approaches. Here s is displacement. If I go with the first approach, where I'm writing it as rate of change of displacement, next step I'll cross multiply this, okay, and then I will integrate this. Now again, when I integrate, on the right hand side, I'll take the limits 0 to some instantaneous time t. So my displacement is going from 0, because where we start from, that is taken as the position from which the displacement starts. So the displacement is 0 at time t equal to 0. Okay. So here, where at time t, we can say the instantaneous displacement that is the displacement from t equal to 0 to t, that particular time interval from to t, is s. So that is the explanation of the upper limits. Okay. So left hand side just becomes s from 0 to s. Right hand side, now remember here u and a are constants. Okay, so integration of something like,
Hello.
is this like, okay, where a and b are constants. So like that over here, integration of u plus at will be ut plus half at square plus c as an indefinite integration, because u and a are constants and t is the variable of integration. Okay, so the right hand side becomes ut plus half at square, and on that the limits are from 0 to t. So on putting the limits, you get the standard third equation that you're used to, which is ut plus half at square. So this is the calculus derivation for this second equation of motion, which gives us displacement s as a function time. And by displacement s, we mean displacement s from 0 to t, that particular time interval, from when the motion has started till the time t. Okay, so this is the relationship between displacement and time in a uniformly accelerated motion. I started this section from here only. So you are familiar with this equation again, S is equal to ut plus half at square. Only now you are seeing how this equation comes by application of calculus, or more precisely application of definite integration. Okay, so Manav, I'll just take you through the steps here. Okay. So see, like suppose we have integration of x dx, that's x square by 2 now. So we have integration of, let's say, 5x dx. We have 5 by 2 x square. So like that, we have integration of t dt. That will be t square by 2 plus c. So if a is a constant, we bring it outside. Okay. That's how we get this. Hope this is clear now, Manav.
Yes, sir, got it.
Okay, good. So what happens is like you are used to doing integration earlier with numbers and all that, and now suddenly there are a lot of parametric terms like a, u, and all that. So sometimes it gets confusing. So that's why you have to be very careful in the beginning that understand in the equation which terms are variables and which terms are constants. So the moment you are taking care of that thing, that in this equation that we've written above, that ds by dt wala equation, or even the integration one, u and a are constants, whereas time is the variable, and on the other side s is the variable. So the moment you're clear about that, then you will not tend to get confused. Okay? Okay, so that's our second equation of motion. And let's look at some examples of application before we move on to the third one. Then we'll talk about the graph also between displacement and time. But first, let's look at a couple of numerical examples. So a lot of the time you will see that, in fact, most of the time in motion along a straight line with uniform acceleration, you are ending up just applying the formula in the question. You have to just understand that what information is given and therefore which formula to use. So suppose we have something very direct like this, that a particle starts from rest with uniform acceleration equal to, let's say, 4 meters per second square along a straight line. Okay. So you want to find its velocity at t equal to 4 seconds. Then you want to find its displacement at t equal to, let's say, 2 seconds, at t equal to, let's say, 6 seconds, and from t equal to 2 to t equal to seconds. So you have to be careful what the question is asking. Okay? And also we want to find its average velocity from 0 to 6 seconds and from 2 to 6 seconds. We have to find the average velocity. So just try this out, people. You can solve this exclusively using the two equations that we just derived. Okay. The first one, which is v equal to u plus at, and the second one, which is s is equal to ut plus half at square. I'm going through your answers, people. Yes, Manav, Vineet, both Manavs. Jitesh, your answers all seem to be correct. Very good. Okay. Okay, so let's start with this thing. So we'll use these two equations that V is equal to U plus AT, and in general S is equal to UT plus half AT square. And in this particular case, our initial velocity is 0 because it's starting from rest, and our acceleration is 4 meters per second square. So the general equation becomes that V is equal to 4t. And the general equation for instantaneous displacement is that it is 2t square. So rest is just application. So now you can see that, for example, for the first part, V at t equal to 4 seconds is just 16 meters per second. Okay. For the second part, you can see that displacement from, at 2 seconds will become 8 meters. Okay. That's the A part. The displacement at 6 seconds will become 72 meters. Okay. Now, by this, we actually mean the displacement from 0 to 2 seconds. This is displacement from 0 to 2 seconds. Like that, this one is the displacement from 0 to 6 seconds. So now this part, the displacement between 2 to 6 seconds, that will become how much? 72 minus 8, or 64 meters. So this is the displacement from 2 to 6 seconds. So this is one of the key things to understand here. Yes, all of you got this correct. Vineet, that's correct. Very good. Anandita, I hope you understood. Maybe some small calculation mistake or something you made in the last part, but okay, now let's come to the third part. So third part, we have to use the definition of average velocity. Average velocity is basically total displacement upon total time. So when it comes to average velocity from 0 to 6 seconds.
72 by 6.
Yes. It's 12 meters per second. Okay. But the average velocity, for example, from 2 to 6 seconds, that is going to be the displacement between 2 to 6 divided by that time interval, which is now 6 minus 2 or 4 seconds. So it is 64 divided by 4.
16 meters.
So this is like a typical application of this situation. Okay, now let's come to something a little bit more tricky. Let's come to an example where there is negative acceleration. So initial velocity is, let's say, plus 40 meters per second along the x-axis. And the acceleration is minus 4 meters per second square. So it is a uniform acceleration along the negative x-axis, or you can say it's a uniform deceleration along the positive x-axis. Okay. So now we have to find displacement after eight seconds, and we have to find the displacement from from, so not 2 seconds, this 12, from 8 to 12 seconds. So we have to find the displacement from t equal to 8 to 12 seconds, and we have to also find the distance traveled from 0 to 8 seconds, 0 to 12 seconds, and 8 to 12 seconds. Now we'll also do one thing. We'll also find the velocity at these two times for both of these. The instantaneous velocity at t equal to 8 seconds and the instantaneous velocity at t equal to 12 seconds. That will also give you some idea about what's happening. Okay, Vineet, have you calculated again?
Yes, sir.
Okay. Okay, so see, as far as displacement is concerned, you can just go for the formula. Okay, so S as a function of time will be 40t minus 2t square. And velocity as a function of time will be 40 minus 4t. So you can use this formula directly for the first part. At t equal to 8 seconds, you can see that your displacement will be how much?
192. 320 minus 128.
Minus, sorry, 28, right? So how much will it be?
192. 192.
So it will be, okay. And our instantaneous velocity will be
8.
but again in the positive direction. So the sign becomes important over here.
Yes.
But for example, at t equal to 12 seconds, you should be getting S as again plus 192, I believe. Is that coming?
Yes, sir. And velocity will be in -8.
But velocity will be symmetric but opposite in sign. Now I'll show you why this is happening also by understanding this whole motion visually. Okay. And which is why you will see that now the second part, the displacement between what is it now, 8 to 12 seconds, that will be 0, but not the distance. Okay, this is the displacement. Now this is going to make the third part pretty interesting, the distance traveled part. Okay. So try to figure that out. Okay, because just as a hint, I can tell you that what's going to happen is that this object is going to initially slow down as it goes towards the positive direction, stop at some particular point of time, and then return back. And as it's returning, its velocity is negative, but its speed is increasing. Whereas while going in the positive direction, its velocity is positive, but its speed is decreasing. So it has a way of, going in one direction, slowing down as it's going, stopping at some instant, and then coming back via that same path. And while coming back, its speed is increasing. Okay, so let's try to visualize this last part like this. Before we get into the distance traveled, let's try to understand the path. It's a straight line path, but it is backing and forthing. So let's understand that aspect by looking at the velocity time graph. Now here in the question, the analysis is not going beyond 12 seconds. So I will just plot the graph for 12 seconds. It can be plotted for longer time also. So the 12-second part will probably look something like this. Okay. So started with an initial velocity of 40 and an acceleration of -4. So what will happen is that it will come to rest exactly in 10 seconds. Whereas at 8 seconds, see that would be somewhere here, the velocity was 8, right? And in 12 seconds, seeing that the velocity is -8. So this kind of situation. So how this graph is helping us? So how I knew the velocity is becoming 0 at 10 seconds? Because v is equal to 40 minus 40. So we can see that v is greater than 0 for t equal to 0 to 10 seconds. I mean, up to 10 seconds. Velocity becomes 0 at t equal to 10 seconds. And velocity becomes negative. That means negative direction. For 10 seconds. So also from the information that we had seen earlier, you can figure out that if it started from here at t equal to 0 with 40 meters per second, then it reached somewhere here at t equal to 8 seconds with a velocity which was positive and equal to 8 meters per second. Thereafter, it is going further like this, coming to rest at 10 seconds. Then it's on its way back. So as it comes back, it crosses this point again, but with a velocity of -8 meters per second at t equal to 12 seconds. That is the story of this part. Okay. So what we'll have to do first now is we'll have to calculate this distance. This distance is how much now? You see, it's
Displacement at 10 seconds.
yeah. You see the displacement at 10 seconds, you see it will come out to be 200 meters. The displacement at 8 was equal to the displacement at 12, which was 192. So now you can understand about this. So this gives us clarity to that part, that as far as the distance traveled is concerned, from 0 to 8 seconds is directly going in one direction. It's traveling 192 meters. Now I won't say plus minus sign because distance is a quantity which does not have direction. So it will not have sign. Okay, like that from 0 to 12 seconds. Now tell me how much the distance will be? 0 to 12 seconds.
208.
Very good. It's going 200 meters up to 10 seconds, then coming back another 8 meters. So the total distance is 200 plus 8 in two opposite directions, but so 208 meters. Whereas similarly, what about the distance traveled between 8 to 12
16
seconds?
meters.
Yes, very good. It's going 8 meters in one direction, then reversing back. So it is 16 meters. 8 plus 8, 8 forwards and 8 backwards. So whenever we have this kind of situation that in a straight line motion with uniform acceleration, the acceleration has opposite sign to the initial velocity. There's always a possibility that the object is coming back. if it's moving for long enough time. Here, suppose the motion was only happening from 0 to 10 seconds or 0 to 8 seconds, then this part would not have happened. But the moment that motion is lasting more than 10 seconds, there is this added complication that its path is reversing. So to analyze distance, we have to do this analysis. We have to find out when the particle is coming to rest and changing direction so that we can individually treat those parts. Okay, so I hope this section is clear to all of you, the graph as well as the visual representation of the motion. We will talk about the displacement time graph also very soon. Okay. Okay. So now, having understood this, let's talk about the displacement time graphs. Again, we are always talking about uniformly accelerated 1D motion today. So again, in this, there'll be two cases. Okay, one where U and A have same sign, and the other where U and A have opposite sign. So we are looking at this graph, S is equal to UT plus half AT square. So we can say that the displacement S is a quadratic function of time. And we have seen earlier that quadratic functions have graphs of a shape which is called parabolic. So they will be parabolic shaped graphs. So the first case, let's say U is plus 20 meters per second and A is minus 4 meters per second square. So S is going to be, oh sorry, let's take plus. Let's take the first case where both are plus. Take the second case where this one is negative. So S is going to be UT plus half AT square. So 20T plus 2T square. So this one is going to look like a graph like this. Displacement time graph always starts from the origin. You never have an initial displacement. That's the way displacement is counted. It starts from S equal to 0 at T equal to 0. So in this case, the parabolic curve will be such that its slope is always increasing. It will be like this. It has a increasing slope. Because what is the slope? V. And V is increasing with time. For example, if I draw a tangent over here compared to another tangent over here, you can see the slope of the tangent has increased. Whereas on the other hand, if I have a situation where our A is of opposite sign, so in this case, A is minus 4 meters per second square, then S will be UT plus half AT square, but that will become minus 2T square. So this will be a parabola with decreasing slope. instead of increasing slope. So my S versus T graph here, that will look like this. So you can also see from this that my V is equal to 20 minus 40. So V is equal to 0 at T equal to 5 seconds. This must be 5 seconds because at this point the slope becomes 0. Whereas at 10 seconds, the displacement again becomes 0. You can see. So in this case, there is deceleration. That is, V is positive and decreasing from 40 meters per second to 0 from T equal to 0 to 5 seconds. And then there is acceleration, but in the opposite direction. That is, V is negative and the speed is increasing from 0 to minus 40 meters per second, from 0 to, sorry, from 5 to 10 seconds, etc. That kind of thing. You can see the shape of the displacement versus time curve will be different in this case because A is negative, U is positive, whereas the first case, A and U were both positive. So in this case, you can see that the slope of the curve is first decreasing. To draw tangents at various points, you can see the slope is decreasing till it becomes 0 at this point at 5 seconds. Okay, and then the slope again starts increasing in magnitude, but it's negative. So while coming back to where it started from, the particle would again be increasing in speed. Okay. Now let's come to the third and final equation of motion. The relation between instantaneous velocity v and instantaneous displacement s. Yes, we have the relation that so this implies that, and this acceleration is constant here. So this can also be written as dv by ds multiplied by ds by dt. So this is the application of chain rule, that the rate of change of v with respect to time can be expressed as the rate of change of v with respect to s multiplied by rate of change of s with respect to time. Okay. And by definition, ds by dt is equal to v. So we can say over here that v dv by ds is equal to a, which is, by the way, constant. So the third equation of motion comes by actually using the chain rule to advantage, cross multiplying this and then integrating. So initially the velocity v was u when the displacement was 0, and at some instant the velocity is v when the displacement is s. So at t equal to 0, the initial velocity was u, the displacement was 0, whereas upper limit at time t, the instantaneous velocity is v and the instantaneous displacement is s. So these are the two unknown quantities. These are the known quantities. Okay. So v square by 2 integrated from u to v will be on the other side a into s, because a is a constant, integrated from 0 to s. So v square by 2 minus u square by 2 will become a into s minus 0, which will give us the relation. Okay, so let's look at an application example or two. We have something like this now that initial velocity of something is, let's say, 20 meters per second, and the acceleration is uniform such that v is equal to, let's say, 40 meters per second at an instant when the displacement is equal to 120 meters. So find the acceleration, the time at which s is equal to 120 meters. Yes, Jitesh, that's correct. There's one more way of deriving this equation by basically using algebra. You can eliminate time between equation 1 and 2. Okay. So basically, equation 1 is the relation between v and t. Equation 2 is the relation between s and t. So substitute the value of t in terms of v from the first equation into the second equation, and you get the third equation of motion. But here I'm showing you the most convenient way of deriving this, and also more sort of general method of deriving it, which is coming from the application of chain rule.
Yes, sir.
Even the first two equations, there are non-calculus ways of deriving it also. For example, from area under the graph and all that. But here, since you've done calculus, so like I'm emphasizing on the calculus method of derivation.
Yes, sir.
Okay, very good. Vineet, that's correct. Manav, that's correct. Jitesh, correct. Anandita, correct. Yes, we can do that, Jitesh. Okay. We can also make use of the second equation of motion also for B part. Okay, whichever we like. Okay. So anyhow, so there are many ways in which this question can be done. So for example, the first method is use this equation. B square is equal to u square plus 2as and fit the data directly. That 40 square is equal to 20 square plus 2a into the displacement, which is 120.
So you can take v square minus u square. So थोड़ा आसान पड़ेगा.
Sorry, we can take
V square minus u square.
exactly. So b square minus u square is equal to 2as, right? That one only. No? See, acceleration comes out to be 5 meters per second. Right? So that's the first part done, and then we can use the second equation. That I mean, we can use the first equation. So or we can use this also. So 120 this will be a bit lengthier, but those will be done. This can also be used. Alternately, we could have also started the question this way, that 40 is equal to 20 plus 80. A is also unknown, T is also unknown, and 120 is equal to 20T plus half 80 square. And then solve these two equations. So that would have been a bit of a lengthy method. So solving for A, for example, from this first equation, we would have taken T as 20 by A and substituted in the second equation. Okay, but that would have been like a two-step approach, whereas using this equation was a direct approach. So this is preferable here. Okay, now we can always have a question where there's a combination of situations happening. Okay, like this, for example, that a particle starts from rest at t equal to 0 with a uniform acceleration of let's say 10 meters per second, and after 8 seconds starts to decelerate uniformly at 5 meters per second square, until it stops. So find the total displacement, the total time, and the average speed, and also the maximum speed during the motion. So this is like not, you can't say it's a uniformly accelerated motion because in between the acceleration is changing, but it's a combination of, you can say two separate motions, two parts of motion, one part with a uniform acceleration of 10 and the second part with a uniform deceleration of 5. So to each individual part, you can still apply the equations. Okay. So just try out this question. We'll discuss some different approaches to this also. Yeah, Vineet, your answers are correct. Anybody else might have worked out a question? So there are a couple of ways we can do this. One is we can just go with a formula based kind of approach and divide the motion into two parts. Part one of the motion is, let's say, from t equal to 0 till 8 seconds. And during this interval of time, you can see that starting from rest, okay, but uniformly accelerated. So at the instant 8 seconds, you can see the instantaneous velocity will be how much now? 80, right? And the displacement would have become 5 into 64, 320 meters, right? Now the second part of the motion, that is from t equal to 8 seconds to some time capital T, suppose we don't know the value. Okay, now for that interval of motion, what is happening? The initial velocity, let's say u prime, that is becoming this velocity. That is becoming 80 meters per second. Okay. And the final velocity is 0 at t equal to capital T. And five meters per second square. Okay. So v prime should be equal to u prime plus 2a prime into that time difference, right, in general. This time interval, this delta t, this is from t equal to 8 seconds to t equal to this interval. Okay. So we have, sorry, plus t. So 2 here. Okay. So this is when the motion stops. And the displacement for the second part, you can see, you can either write it like this, where that delta t is now our 16 seconds, or t minus 8. Okay. Or we can also use this, that use this also. Okay. So you can do this way also. So now you can see that the net displacement
So the S prime will be minus 640, right?
nahi beta, it's not coming back. See na, understood the point na? Its velocity is going from 80 to 0 na. Its velocity is not becoming negative. You're following my point na?
Yes, sir. But
So the displacement is not becoming negative na? And in this also you can see the formula also is not becoming negative. See, both
yes,
the
sir.
approaches, it's not becoming negative. What was the displacement in the first part? It was much we got 320 now. Yeah, so 320 plus 640. So both the distance and displacement are the same in this case. It is 960 meters, the positive direction. Okay, so this is one way of doing the question, but I would prefer not doing the question by this method because I have wasted too much time in applying the formula and all that. I'll show you a quicker way of analyzing the question using a sort of calculus way of understanding it or a graph way of understanding it. Okay. So I'll come to that also, but first you can just go through this and make sure all the concepts are clear. Okay, so people, I hope this approach is clear to the question for all of you. Okay, now, as I was saying, the preferable approach I would take is to make use of the concept of change and graph and all that, because that would make this problem much faster. So if I instead visualize this graph, visualize this problem as a V versus T graph situation. Okay. The whole problem I'm converting into visualizing the graph of V versus time. So what I understand, it starts from rest. Okay. And that is at t equal to 0. then it accelerates uniformly at 10 meters per second square for 8 seconds. Okay, and then it decelerates uniformly at 5 meters per second square till it comes to rest. And that is at some time capital T which I don't. So what I will do now is I will visualize this as what is happening in my V versus T graph. That's pretty easy to visualize because at least the rate of change of velocity is uniform. So it's, it will be, each part will be a straight line graph. So the first 8 seconds will look like a straight line graph with a positive slope starting from 0, right? Let's say it's having an acceleration of plus 10. So it will reach a velocity of 80, which by the way is also the maximum velocity, which I'm sure all of you figured out. But now the next part now is decelerating at 5. So immediately you can understand this, the slope will be less steep. Understand now that it's decelerating. So I'll write this as A prime equal to minus 5 meters per second square. So from the graph, you can now make out that, these two triangles, their slope is such that, this value of time, this delta T prime, let's say, will be double of this delta T. Delta T prime is going to be 2 times delta T because the second graph slope is minus 5, the first graph slope is plus 10. Okay. So from that you can understand that this time T is such that T minus 8 seconds is equal to 2 times 8 seconds. You see that T will become 24 seconds. And then you can see that the total distance covered is just the total area. That is half into T into V max. This is our V max. Which is the same thing as actually displacement. So this is all about application of uniform acceleration in straight line motion. Albeit in this particular question, we are saying it's a two-part situation. Each individual part has a individual value of uniform acceleration or deceleration. Okay. So here's where we conclude today's lecture. Next time we will see some more general things in straight line motion again, including variable acceleration. And then we will move on to the particular application of this situation when there is vertical motion under gravity. So it can be free fall of an object, or you throw an object vertically upwards, so it goes up in a straight line and comes back in the same straight line. So we'll see vertical motion and finally moving on to projectile motion. So that's it for today's session, people. Thanks for attending the show.
Thank you, sir. Bye, sir.
Okay, people. Bye.
Thank you, sir. Bye.
By-Shome.